like math. Sometimes when people are starting out in biology, for some reason they assume there is no math in biology, but then they soon find out they were wrong. My math teachers were telling the truth when they said math isn't everything. Chi-squares, osmotic pressure calculations, standard curves with gel electrophoresis, Punnett square ratios, these all have math. But one of my favorite topics that involves biology and math and is also absolutely fascinating is the Hardy-Weinberg equilibrium. It got its name from a mathematician and a physician, and it states that a population's allele and genotype frequencies are constant, unless there's some type of evolutionary force acting upon them. A reminder from our ecology videos, a population in this case is a group of organisms that are all the same species and can breed with each other and have fertile offspring. However, there can be variety among a population as they're not clones of each other, but based on Hardy-Weinberg equilibrium, the population's allele and genotype frequencies would remain constant if no evolutionary force acts upon them. If we have these frogs here, assume they are all the same species in this example, but there are some slight differences. In our simplified example, some of the frogs are lighter green and some are darker green. We're going to use a simple genotype in this example. All frogs in this population will be either big G, big G, little g, or little g, little g. There's also an allele frequency in our population. We're going to say here that 60%, a frequency of 0.6, of the alleles are big G. 40%, or a frequency of 0.4, of the alleles are little g. Notice the percentages add up to 100%, and the frequencies add up to 1. Now, to be in Hardy-Weinberg equilibrium, we have to have 5 assumptions. Number 1, no selection. No natural selection is acting upon these frogs. That means neither dark green nor light green will have any impact on reproductive fitness. Number 2, no mutation. Baby frogs inherit genes from their parents and there are never mutations. Number 3, no migration. Frogs can't come in, frogs can't go out. Number 4, large population. There are a lot of frogs. It turns out small populations are more vulnerable to genetic drift, by the way. See our genetic drift video. Number 5, random mating. The frogs mate without any specific choice. All of these 5 assumptions must be kept in order for Hardy-Weinberg equilibrium to happen. So, in real life, does this generally happen? No. For example, in real life, maybe in a certain environment, predators can more easily see the light green frogs, so perhaps they are eaten more and have less reproductive fitness. So if Hardy-Weinberg equilibrium is unrealistic in nature, why does the Hardy-Weinberg equilibrium matter? That's where the math comes in. The Hardy-Weinberg equilibrium gives you this baseline to compare how an evolving population could compare to one that remains constant without evolutionary forces acting upon it. And now let's explore the math. So there are 2 equations in Hardy-Weinberg equilibrium that we will focus on. We're going to start with the first one. P plus Q equals 1. In this equation, P is the dominant allele frequency in the population, and Q is the recessive allele frequency in the population. By the way, Hardy-Weinberg equilibrium doesn't mean that P has to equal Q, and the dominant allele frequency in any population doesn't have to be larger than the recessive allele frequency in a population. That's a misconception because dominant alleles aren't always the more common allele. The equation does say that the dominant allele frequency and the recessive allele frequency have to equal 1. So, in my example here, if I say 60% of the alleles are big G, 40% of the alleles are little g, 0.6 is P, and 0.4 is Q. So this equation, P plus Q equals 1, is for those allele frequencies. But what if I wanted to know the genotype frequencies? Meaning, I wanted to know the frequency of frogs that are homozygous dominant, which is big G, heterozygous, which is big G, little g, or homozygous recessive, which is little g, little g. Then I can use this other Hardy-Weinberg equilibrium equation, P squared plus 2PQ plus Q squared is equal to 1. So P squared is the homozygous dominant frequency, the frequency of big G in this case. 2PQ is the heterozygous frequency, so big G, little g frequency in this case. Q squared is the homozygous recessive frequency, so little g frequency in this case. Let's plug those previous P and Q values in. P squared would then be 0.36, 2pq would be 0.48. Q squared equals 0.16. Cool, huh? The only thing is that when calculating Hardy-Weinberg equilibrium problems, you don't always have the p and q values. So we're going to do an example. New population of frogs, so forget the previous frequencies. This is a new frog population in a new frog land, but we'll still use the same allele letters. So here's the information you get for this new population. There are 500 frogs, and of those, 375 frogs are dark green. The rest are light green. With that information, please solve all genotype frequencies and all allele frequencies if in Hardy-Weinberg equilibrium. Step 1. Determine first whether you're going to work with the first equation or the second equation. Since I'm working with individuals here that have genotypes, I'm going to work with the second equation first. Step 2. Figure out what value you can determine. So 375 frogs are dark green out of 500 total. That would mean 125 frogs are light green since there are 500 frogs total. But I can't use whole numbers like that, as both of these equations ultimately are equal to 1. I need frequencies for these equations. Now, I could say 375 dark green frogs out of 500 total frogs is 0.75, but all I know is that would be the frequency of dark green frogs. The problem is dark green frogs could have genotype big G, or they could have big G, little g. I can't assume they're one genotype or the other, so I shouldn't use that value. The recessive genotype, resulting in a light green trait, is safe to use though, because I know that light green frogs are the genotype little g. They can't be anything else. So 125 frogs out of 500 frogs equals 0.25. That means, from the equation, the value q squared equals 0.25. Step 3. Take a value you solved from the previous step and calculate from there. So if I know that q squared is 0.25, then I could go ahead and solve for q. If q squared is 0.25, I can determine q if I take the square root of 0.25. Therefore, q is equal to 0.5. That's the allele frequency for the recessive allele little g. If I know the q value, I can find out the p value using the first equation. Since p plus q is equal to 1, now I know that p is equal to 0.5. That's the allele frequency for the dominant allele, big G. Now I have p, and I have q, and I can take care of everything else. I can use the second equation to determine the homozygous dominant frequency, the heterozygous frequency, and I already knew the homozygous recessive frequency from the beginning. Plugging those in, p squared equals 0.25 for the genotype frequency big G, 2pq equals 0.5 for the genotype frequency big G, q squared equals 0.25 for the genotype frequency little g. Phew, that's a lot. Finally, some last tips for solving Hardy-Weinberg equations. Number 1, I used nice numbers, meaning I didn't need a calculator for my examples. It's not always like that. You might need a calculator for the numbers you're given, and you might need a round. Number 2, when you get your final results, always check that the values you calculated do equal 1 for both equations. This can really help you check your work. Number 3, be careful not to assume too much with given info. Remember when I was given a value of 375 frogs out of 500 being dark green? I didn't necessarily know whether they were big G or big G, little g. Instead, I chose to work with the recessive genotype since I knew light green frogs would be little g. Number 4, practice. There are a lot of practice problems you can find online, and remember, this skill can be very useful for determining the extent of evolutionary forces because you have this base comparison of Hardy-Weinberg equilibrium to compare it to. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.